In the previous lecture, we started from definition 2 of the Poisson process, which was the Baby-Bernoulli definition. And we arrived at an interesting conclusion. We discovered that the total number of arrivals in a time interval, n of t, has the Poisson distribution. Let's try to recap and recall the Poisson distribution. A random variable is said to have the Poisson distribution with mean A if the probability, and this should be y, the probability that y takes on the value k is given by a to the k e to the minus a over k factorial for values of k equal to 0, 1, 2, etc. So it's an integer valued, non-negative integer valued random variable. The mean A appears here and here, if you notice. Let's see, the moment generating function for this distribution is given by my of s equals e to the a e to the negative s minus 1. Now, in the previous lecture, we did a differential equation argument, and we arrived at the function e to the lambda t e to the negative s minus 1. By the way, there was a typo at the end of the last lecture, and this should be negative s. And we realized that as this was the moment generating function of the number of arrivals, the number of arrivals should be Poisson with mean lambda t. Right. So, maybe we can use this to make another alternative definition for the Poisson process. Now, recall that a moment generating function fully determines the corresponding distribution, by the way. So that's why we concluded that based on the moment generating function, we concluded that n of t should be Poisson with mean lambda t. So here is the definition. Let's call this definition 3 of the Poisson process. A counting process n of t that starts at 0 and goes indefinitely is said to be a Poisson process with rate lambda if the process has stationary and independent increments, and for any time instance s and t, the probability that the difference between n of t plus s minus n of s is equal to k is given by e to the lambda t to the k over k factorial. Meaning, the probability that there are exactly k arrivals from time s up to time t plus s is given by the Poisson PMF with mean lambda times s, lambda times t, where t, remember, is the size of this interval. The interval from s to s plus t has size t, and the expected number of arrivals, it turns out, is equal to lambda times t. Now we can show that this definition, definition 3, implies definition 2. What was definition 2? The Baby-Bernoulli definition. How can we show that this definition implies definition 2? What was definition 2? A counting process is a Poisson process if n of 0 is 0, if it has stationary and independent increments, and also if the probability of an arrival, one arrival in an interval of size delta is lambda delta plus little o of delta. The probability of no arrival is equal to 1 minus lambda delta plus little o of delta, and probability of more than one arrival is little o of delta. How can we go from definition 3 and show that we obtain definition 2? Very easy, right? Just plug it in to the Poisson. Plug delta in, right? So, definition 3 says that n of t, if you want n of delta is Poisson with mean what? With mean, if you want, let's stick to the same notation, s to s plus delta. S to s plus delta, size delta. It's Poisson with mean what? Lambda delta. Right? So the probability that n of delta is equal to 0 is equal to e to the minus lambda delta lambda delta, right? Lambda delta to the k over k factorial evaluated at k equals 0, which is e to the minus lambda delta. But think about the Taylor series expansion. According to the Taylor series expansion, this is 1 minus lambda delta plus O of delta. Okay, how about the probability that n of delta is equal to 1? Let's see. This is, this evaluated at k equals 1, right? E to the minus lambda delta to the 1 over 1 factorial, which is, let me erase this part. What? Lambda delta e to the minus lambda delta. Again, use the Taylor series expansion for this term. Lambda delta, 1 minus lambda delta plus O of delta. What do you find? Lambda delta minus lambda squared delta squared plus lambda delta O of delta. But all of these terms is O of delta. Okay. Clearly, then the probability that n of delta is bigger than 1 is O of delta. So we have shown that definition 3 implies definition 2. Any questions? Now, definition 2 already implied definition 3, right? Because that's how we obtained definition 3. So then they both imply each other and they are equivalent. We already know that definition 1 implies definition 2, although we didn't really formally show it. Let's show that definition 3 implies definition 1 by using, let's show that definition 3 implies definition 1. Let x1 be the time until the first arrival in the process in definition 3. It should be 3. Okay? Compute the CDF of x1. And then compute the CDF of xi for I bigger than 1. Can we show that they are going to be exponential? How do we do that? Now, let's show that definition 3 implies definition 1. So, what does definition 3 tell us? Definition 3 tells us that n of t is Poisson with mean lambda t. And this is x1, the time of the first arrival. Or let's just do this. Suppose this is time t, this is time t, and this is x1, the time of the first arrival. And probability that x1 is bigger than t is the same as the probability that n of t is equal to 0. That you already know that. Same argument we used before. And now plug it in the Poisson PMF, lambda t to the 0, e to the minus lambda t over 0 factorial. And that gives us e to the minus lambda t. So done. So clearly x1 is exponential with rate lambda 1. What do we do about the further interarrival times, xi's? How about x2? x2, remember, is the duration from x1 up to the next arrival. But by the independent increments property, this increment from this time until that time has the same distribution as an increment that starts at time 0 and has that duration. So the probability that x2 is bigger than t is the same as the probability that n of t equals 0 by the stationary and independent increments properties. So clearly xi is exponential with rate lambda. I'm sorry, this is not lambda 1. This is lambda for all I. So this shows that definition 3 implies definition 1. So basically this implies definition 1. If you also show this, you show the equivalence of all of the definitions. Now, but rather than focusing on the equivalence of all of these definitions, let's see how we can use the Poisson process on interesting examples, as well as learn a little bit more about the mechanics of this Poisson process. Let's just focus on this example for the moment. Suppose I get email according to a Poisson process, meaning emails come into my email server according to a Poisson process. Now, let's just do a brief detour. Why do you think the Poisson process may be a good model for email that I receive? Okay, what is the Poisson process? It's good sometimes to think about it in terms of the Baby-Bernoulli definition. In every little interval, the probability that I get email is small, and it doesn't matter where the interval is, and all little increments are independent of each other. So at any time, I'm getting email randomly at a constant rate. Why do you think this can be a good model for the email that I receive? It may or may not be, but suppose I get email from all over the world in every time zone, which is, you know, not very far from the truth. Maybe I get more emails from my local colleagues, but I also get emails from international colleagues and organizations, etc. Suppose I get email that originates randomly from people or organizations independently of each other in time. And it can happen with equal rate during any time during a 24-hour period, because everybody sending email to me is supposedly acting independently of each other. And each particular person or organization is unlikely to send me email at any given particular moment. So the aggregate of all of those effects can be quite well modeled using a Poisson process, because they are each very little effects occurring independently of each other. Now, it may not be a good model. The Poisson process may not be a good model for the email that I receive, but there are many other situations where the Poisson process will be a good model for. All right. Then suppose that is a good model, and suppose that's the model I'm adopting. I get email at the rate lambda equals 1.5 arrivals per minute. All right. Should I check my email every hour, or should I check less often? If I check my email every hour, what is the expected number of messages I find in my inbox when I check my email? What do you think? What is the probability that I find no messages? What is the probability that I find one message or no messages if I check every 2 hours? So, probability one message in 1 hour, in a 1 hour period, is, well, in our language of the Poisson PMF, this is n of t is 1. What is t? T in this case, in terms of the number of minutes, is 60 minutes. Right? Because I'm counting time in minutes. All right, so, well, that is lambda t. What is lambda t? Lambda t, if you want, lambda t to the 1 e to the minus lambda t over 1 factorial, where lambda t is 1.5 arrival per minute times 60 minutes, right? 1.5 arrivals per minute times 60 minutes, right? What is that? 90. So, then this is 90 times e to the minus 90. Okay, what is the probability of 0 messages? Lambda t to the 0, right, over 0 factorial, e to the minus 90. Pretty small. Okay. Now, how about I repeat for 2 hours? Probability of one message in 2 hours is, this time, k equals 2, right? Lambda t is 90, so 90 squared e to the minus 90 over 2 factorial, which is 90 squared over 2 divided by e to the minus 90, and probability of 0 messages in 2 hours is, well, e to the minus 2 hours. Right, lambda t is not 90. What am I saying? Lambda times t is now 180. Right? 180 times e to the minus 180. This is 0 messages in 2 hours is 180 to the power 0 e to the minus 180. So 0, right? So now let's talk a little bit about the waiting times until we get an arrival. We talked a lot about the distribution of the total number of arrivals at an interval. Now, how about the time of the nth arrival? Remember, in the beginning of our discussion on the counting process, we talked about Sn, the number of arrivals, the time of the nth arrival, and the number of arrivals, n of t. Okay, so how about the distribution of Sn? Sn, of course, is the sum, given by the sum of the first n inter-arrivals xi's. And we will show that this thing, the sum of n independent identity distributed exponentials with rate lambda, obeys the Erlang distribution of order n with parameter lambda. And it's this distribution, which of course you don't have to know by heart, but we can easily show this. Let's just show it. Yes, please. No, I made, right, one message, yes, thank you. So let's erase this part. Okay. So now Sn is the sum of xi's. Compute the density of Sn. In order to do this, we will start from the CDF of S sub n. Okay. And basically we will say Sn of t is the density of the probability that Sn lives between t to t plus h. I mean, sorry. This is more like it. It's the density of the CDF. In other words, it's the limit of the probability that Sn lives in a tiny interval of size delta, size h, I'm sorry, normalized by h, in the limit as h goes to 0. Okay? So let's compute the probability that Sn lives in this interval. And we are going to interpret this event in terms of the number of arrivals. So if you will, again, let's draw a picture. This is t, and this is t plus h. And I'm looking for the event that the nth arrival happens somewhere here. In order for the nth arrival to happen somewhere here, first I need n minus 1 arrivals before that and 1 arrival here. So basically, because since, I mean, if you, as you know, the event Sn is less than or equal to t, is the same as the event that n of t is bigger than or equal to n. So if Sn is bigger than t, this means that n of t is less than n. So here, n of t cannot be equal to n. It can be at most n minus 1. So this is the probability that n of t is equal to n minus 1, and there is one event in t to t plus h, plus a number of other events with probability very small with respect to delta. I mean, with respect to h, the size of our interval h. Okay? So, but then, since this interval, oh, use a color, this interval and this interval are independent, I can split this probability of the intersection of two events as a product of probabilities. Probability that n of t is n minus 1 times the probability that there is one event or one arrival in t to t plus h plus O of h. This I already know as lambda t to the n minus 1 e to the minus lambda t over n minus 1 factorial. Remember, I'm using definition 3. And this is the probability of one event, one arrival, and that is given by lambda times h plus little o of h. Okay? So when we sum up this whole thing, we find lambda e to the minus lambda t times lambda t to the n minus 1 h divided by n minus 1 factorial plus little o of h. And now I'll divide by h and take the limit as h goes to 0. So I will basically, I can just write it over here. When I divide this by h, this h will go. And when I divide this by h and take the limit, it will go to 0. So this limit then is nothing but lambda e to the minus lambda t to the n minus 1 divided by n minus 1 factorial. And this is known as the Erlang PDF of order n with parameter lambda. Erlang of order n. So let's apply it to something easy. This is, suppose this is x1, this is x2, and this is s2, the time of the second arrival. S2 is equal to x1 plus x2. What is fs2 of t? This is the density function of the second arrival time. Plug in 2 here. what do we get? Lambda squared t e to the minus lambda t divided by 1 factorial, which is 1. So this is Erlang of order 2 with parameter lambda. To do a sanity check, how about let's plug in n equals 1. We get 0 here. So lambda t to the 0 is 1. This is 0 factorial. Lambda e to the minus lambda t, which is what we expect. It's the exponential PDF. Okay, so now we know a number of things about the Poisson process. We're really getting to know this process. We know that the inter-arrival times are exponentials. We know the fresh start property at any time the process starts over. We know that in any interval, the expected number of arrivals is proportional to the size of the interval, and the constant of proportionality is lambda, the rate of the process. We also know that the distribution of the number of arrivals in an interval is Poisson with mean lambda times t. And lastly, we know the density of the nth arrival time is Erlang of order n. We know a lot of things now. Now it's time to reuse these in problems. So here is the next problem that we are going to try to address. And maybe we can check the problem statement. Suppose starting at time t equals 8:25, students start arriving for the 8:40 class. Okay, but let's not limit the time at 8:40, of course, otherwise we will not get a Poisson process. Suppose this process continues at a rate of 1 student per minute. Okay, find the distribution of the time elapsed up to and including the arrival of the 10th student. What do you think? So at 8:25, students start arriving, and then in part A, we are asked for the time elapsed up to and including the arrival of the 10th student. So this is S10, right? S10. And we know that this is Erlang of order 10 with parameter lambda. And you can easily plug it into the Erlang density. Now, let t be the time elapsed between the second and the fourth arrivals. This is the second arrival. This is the fourth arrival. T is the time elapsed between the second and the fourth arrivals. What is the probability that t is bigger than 2 minutes? Probability that t is bigger than 2 minutes. Well, what is t? T is x3 plus x4. Okay? This is the probability that x3 plus x4 is bigger than 2 minutes. What is the distribution of x3 plus x4? Erlang of order 2. Right? It's the same as the distribution of S2. So let's recall our Erlang PDF. So this is the integral of S2 of t dt, t from 2 to infinity, right? What is fs2? We already computed it here. in our case, lambda is what? 1 arrival per minute. What is t? T is t. T is a free variable. So that was a trick question. Right? So, to the infinity. Maybe let me leave it for as lambda for now. Lambda squared t e to the minus lambda t dt, where lambda is 1. So this is integral from 2 to infinity t e to the minus t dt. Very easy to compute. Okay. So write an expression to compute the third moment of t. The third moment of t. What is the third moment? That's the expectation of t to the, t cubed. Now that's a trick question. How do you?
Can you think they're independent? So.
Very nice. Very nice. Well, we noticed that t is the sum of x3 and x4, right? Okay, but these are IID exponential. Because they're independent, the moment generating function of the sum is the product of the moment generating functions. So mt of s, the moment generating function of t, is equal to the moment generating function of x3 squared, because moment generating function of 3 and moment generating function of 4 are equal. And what is it? It's lambda over lambda minus s, if I'm not mistaken. And how do you compute the third moment? This is differentiate the moment generating function 3 times and evaluate it at 0. Right? So d by ds cubed mt of s evaluated at s equals 0. And you can easily do this. Okay, now let's, before we end, let's talk about the reversed process. Okay. It turns out if we reverse a Poisson process in time and look at the arrivals going backwards in time, we observe a Poisson process again. And it is not very surprising, and it follows from the memorylessness of the exponential distribution. We can show that the reverse residual time distribution is the same as the inter-arrival time distribution. Well, I mean, the argument is the same as we did for the finding the distribution of the residual life. So what we mean is if I'm looking at the Poisson process, watching the Poisson process, and these are the arrivals. If I'm at a certain t, time t, and look at the time r prime, going backwards in time to the most recent arrival before time t, this r prime can also easily be shown to be exponential with rate lambda. Meaning then the process looking backwards in time also is a Poisson process. We call this reversibility. That is trivially true for the Poisson process. There are other processes that are reversible. That's for graduate school, right? But now we will use this idea to solve some problems in this course. Okay. Go back to the bus problem. At time t, I arrive, and I'm going to get on the first bus that arrives after me. Now, how long do I expect to wait? You already know that. If the bus arrivals are at rate lambda, I expect to wait 1 over lambda. In the previous example, the bus arrivals happened every 10 minutes on average. So expected waiting time is 10. But what is the expected duration of the inter-arrival time that I arrive in? That is going to determine how crowded the bus I'm going to get on is going to be. So question asks something interesting. What is the expected number of people on the bus that I'm going to get on? Of course, the problem is not well specified. The problem has to tell us something about the process of people's arrivals, right? Suppose people arrive regularly, like 1 person every minute, right? Then, how many people do you expect to be on the same bus as you? Now, that's a tricky question. And we will sort of address it more fully in the next lecture, but I just want to give you a highlight. I arrive here. And this is the waiting time until the next bus. Let's call this R. And the total duration between the 2 buses is R plus R prime. I already showed that R is exponential with rate lambda. R prime is exponential with rate lambda. So what is the distribution of R plus R prime? It's Erlang of order 2. What is the expectation of R plus R prime? One over lambda plus 1 over lambda, 2 over lambda. So in the bus problem, 20 minutes. So what is going on? Bus arrivals are on average 10 minutes apart, but I arrive randomly, and in the inter-arrival time that I sample, the expected size of that inter-arrival time is 20 minutes. Is it because I'm very unlucky? What's going on? Excuse me?
It's a reverse process. You solve the first question in the lecture.
Right. The reverse process is also Poisson. The forward process is also Poisson. When I sample the Poisson process at random, the inter-arrival time that I sample turns out to have mean 20 minutes, not 10. That is interesting. It's called the random incidence paradox. It sounds like a paradox, sort of, but it is not a paradox, of course. It has a perfectly good explanation, which we will talk about in the next lecture.
This equation is seen by us, right? We have 2 intervals actually, R and R prime, but the sum of it we are more likely to sum of these intervals. So that's why it's 2 to n.
Here's the catch. If you average over all inter-arrival times, the mean is 10. Okay? But in that average, small inter-arrival durations and large inter-arrival durations are counted, each is counted once. When you arrive randomly, you are more likely to sample larger inter-arrival intervals. Think about it, and then we will fully address it next time.